Okay. Hello, everyone. Welcome to the second Learning at Lambert Labs session. And today's presenter is Ramin. So I'll hand over to Ramin.
Yeah, thanks, Aaron. So today I'll be showing you what WebAssembly is and how to actually use it. But before we start, WebAssembly is essentially a way to run native code within your browser. So things like C, C++, Python, alongside JavaScript. So that, of course, brings up the question, what's wrong with JavaScript? The first complaint you might have with JavaScript is it's implementation dependent. All that means is there's no source distribution of JavaScript, the way you have with Python 3.8 or C99, for example. This is because JavaScript is actually based on something called the ECMAScript standard. So here we see ECMAScript 1 all the way through 6. ECMAScript tells JavaScript exactly what it should look like, but it doesn't tell it how it should be implemented under the hood. So what this means is every browser actually has to have their own virtual machine capable of running JavaScript. And this causes unpredictability. So here we have a graph. This is JavaScript, a JavaScript file running in Chrome, the same file running in Firefox, and the same one running in Safari. These are the times measured. And you can see that there's about a 2-second delay in timings in Firefox, which is completely unacceptable, especially if we're talking about graphics applications or any kind of time-sensitive code. On the bottom, we have WebAssembly. So you can actually see, first of all, it's much faster than JavaScript. Second of all, the performance is much more predictable. Okay, so that brings us to our next point. JavaScript is inherently slow. It's not designed to be fast. It's designed to be a scripting language in the context of the web. And on the web, a web page needs to load quickly. So what that means is JavaScript can't be compiled by the browser. It would simply take too long. It also can't be compiled on the back end and then passed to the browser because that would introduce security risks. It also can't be interpreted, again, too slow. So in this case, we see the V8 engine, which is Chrome's virtual machine that runs JavaScript. They came up with a 2-step process. So first, they interpret the JavaScript code when your page loads. And then when your JavaScript actually has to execute, only then do they optimize it into optimized machine code. This uses a bunch of heuristics, which is why we see this kind of unpredictability in performance. But it is the best way that we currently have to run JavaScript because it ensures that it's fast to generate, fast to execute. So again, this is a limitation of the fact that JavaScript is designed to be used in the web, designed to be used as a scripting language. The final complaint we might have is we are forced to only use JavaScript on the front end. If you have backend logic that's Python, you have to replicate it on the front end. If you want to use math libraries from C++, you simply can't. If you want to take advantage of the type safety of Rust, again, you can't. So the solution to all these problems is WebAssembly. So WebAssembly is a binary target. You can take any code base that you have, compile it into WebAssembly, and then embed it into the web. So it's called WebAssembly because it is an assembly language, but for a stack-based virtual machine. So it's not a real computer. The way this was designed was to be as close as possible to the assembly language of real-world devices. So what that means is that only a very small amount of information is required to turn WebAssembly into real-world assembly language. So it's as close as possible to native machine code. But it is imperfect. So it has around a 20% trade-off. So if you take a C file compiler to WebAssembly, you'll be around 20% slower than the real C code. If we compare that to asm.js, which is a very strict subset of JavaScript that only allows numbers, that's around 50% slower than native code. And pure JavaScript is around 400% as slow. So this 20% trade-off is looking really good, especially considering the portability that we have. Also, because WebAssembly binaries are very small, the startup time for the virtual machine is actually much smaller than the startup time for the corresponding JavaScript engine. So in this case, V8. So the WebAssembly virtual machine is actually better by 2 orders of magnitude, which is just a huge improvement. So let's actually look at WebAssembly practically, how it works under the hood. You don't really need to know this, but I think it's good to know. So there are 4 data types, 32 and 64-bit integers. That's all you have. You don't have strings or anything else. This just ensures that everything is kept very simple. The computational model is a stack-based virtual machine. So we have an empty stack, and we can push data onto the top of it, and we can pop data from the top. But those are the only 2 operations that we have access to. So let's actually work with this practically and see what it looks like. So I'll go into this file, add.wat. WAT is short for WebAssembly text format. So I don't actually want to write binary. I'm not smart enough to do that. So I actually have to use a text format. The simplest WebAssembly module is simply module in brackets. That's all it is. We can actually see what this looks like in binary. So if I type WebAssembly text to WebAssembly, so this will convert it into binary, and then I pass in add.wat -v. It will hopefully work. Whoops. WebAssembly text. Let's see. I have to actually go into the directory. What was yeah, okay. So this is the binary instruction set. You can see it only has metadata because, of course, our model is empty. So here we have the binary version. Here we have binary magic. Not sure what that is. But now let's actually write a very simple function, which takes two numbers and adds them together. And hopefully we'll illustrate what I mean by stack-based virtual machine. So first of all, this uses S expressions. So this is the parent node of this tree. I will now create a subnode just by adding two brackets. Let's enter a space. So I want to declare a function, func. I'll call it add.assign add. It will take a parameter. Let's call it A, and it will be 32-bit integer. Of course, the second one, let's call it B, very natural, 32-bit integer. And then the result will also be a 32-bit integer, I32. Okay, now the function body is where the stack comes in. So we will push A onto the stack, push B onto the stack. So we do that using local.get. We push A onto the stack, and now we push B onto the stack. At this point, we want to add these two numbers together, but we don't have to specify that we want to add A and B together because we've already pushed them onto the stack. All it can do is take data at the top of the stack, and 32-bit integer addition is already defined to be between two elements. So it already knows, take the two top elements from the stack. So all we have to say is i32.add. We don't need to specify any inputs. In maths, you might have come across this. It's called Polish notation. And yeah, so this is an entire module. And we can actually look at this and what it would look like in binary. So again, we can type what to wasm add.wat -v. This is what it would look like in binary. So it's around 30 lines of code. You can see that it does a lot of setting up. And then at the bottom, does it run the code? And finally, it exits. But remember this, it's around 30 lines of code. That's quite important to remember, because next we're going to write exactly the same file, but in C. So in C, it's much easier to implement int add, int A, int B, return A plus B. So of course, we're adding two numbers together, returning, nothing special there. But we can actually compile this into WebAssembly. So I'll use something called the mscripten compiler, which compiles C and C++ into WebAssembly. So I'll type emcc add.c -s wasm =1, and hopefully that will compile. Let's see. Yes. Okay. And you can see here a.out.wasm is our result. So now we can actually type wasm to what, so convert this into a text format, and I'll just pass in that module, and you'll see that it's much longer. It's a very long file. Okay, not very long, but comparatively very long. And the reason for that is we've compiled from C. So now there's an additional part of the runtime that's being included in this code that wasn't previously. Of course, writing pure assembly language will always be superior. So this is just something to keep in the back of our minds. So if we were to use Python, the runtime environment would be much larger, resulting in a larger binary size. All right, but now we want to actually run C++ or C. I've chosen C++ for this example, just to keep it varied, on the web. How do we actually run this on the web? So in this example, I've written some C++ code. You don't need to worry about this part of it. You don't even need to worry about this part. This is really where the magic happens. We just have a very simple function, add. It takes two strings, A and B, concatenates them on the space, adds an exclamation mark at the end, just keeping things simple. Now, the code around it does something very special, which in the future won't be required, but is right now. So I mentioned that WebAssembly only understands 32-bit, 64-bit integers and floats. So we actually need to include this binding header file. And what this does, it allows us to use strings or any other kind of data type. We can even use image graphic libraries from C, and they will just in C++, and they will just port over into the corresponding web APIs. At the bottom, I have this bindings thing, which actually allows me to export the function so that JavaScript will be able to use it. Now, at this point, I will want to compile this. So I'll compile it using, again, mscripten. I will have to pass a bind option, and I will compile hello.cc. I want to use WebAssembly as opposed to asm.js, and I'll call the output hello.js. Whoops. Oh yes, of course, I need to switch directories. Okay, this is compiling, compiled. All right, so here we have the output. We also have a JavaScript glue code. Now, this might look like a lot, but most of it actually isn't required. It's just a bunch of error handling happening here. And this allows JavaScript to call the WebAssembly virtual machine. So again, most of this is boilerplate code. I could just as easily narrow this down to around 10 lines of code, not necessary. But for now, I'll just include it. So at this point, I've written an HTML file. I wrote this earlier. I don't want to write HTML right now. And here I've referenced the glue code as a script tag. I then have two inputs, text boxes, and I have a button. When clicking this button, I execute module.add on the two text inputs. Module is the object that refers to our WebAssembly code, and add actually refers to our C++ code. So it's referring to this function right here. And hopefully this works. So now I'm going to run a server. Okay, so I've started a server using serve. And I'll navigate to my localhost. Okay, hello.html. All right, we see two text boxes. I'll write hello world. And hopefully we'll see that with an exclamation mark. Yes, perfect. Okay, so that worked. And as you can see, we use C++ code on the front end. This button invokes C++ code as opposed to JavaScript. And I think that's just really beautiful. All right, let's see. Now, what are some of the use cases? Well, here we have something called AutoCAD. Any engineer is really familiar with this design software. It's been around before the web even existed. And what they wanted was to take their C++ libraries and not throw them away, not have to re-implement everything in JavaScript. So they did was they created the interface in JavaScript, HTML, CSS, but all the hard processing is still done in C++. So here you can see we have AutoCAD in a browser. And I think that's the right way to approach WebAssembly. It's not to use WebAssembly wherever possible. It's to find bottlenecks within your JavaScript, implement them in something like C, C++, Rust, and then invoke those. But now here's a question. Can we run Python on the web? Python's a little different because it has a separate runtime. It's, of course, not a compiled language. But in fact, the solution does exist. And I think it's mature enough at this point to discuss. Let me just close a few tabs. So to run Python, we actually take a different approach. We use something called Pyiodide, which is, again, a WebAssembly port. But we can simply use a script tag to include it. So this is a JS file, which will be able to invoke the WebAssembly virtual machine and then run the Python runtime environment. What I've done here is I've actually waited for the language to load. Then I import the system, and I just print the system version, just so we know what we're running. I then actually load a package called NumPy. NumPy you might be familiar with in Python, just allows you to do arrays and matrices. Then I import NumPy, and I run this function here. So I print the addition of two different NumPy arrays. Again, this is purely JavaScript. So let's see if this works. So I'll navigate to the directory, and then I will run serve, and I'll go back into my server. And we should be able to see Python code execute in the command line. So I've opened the console. Okay, that's not working. Okay, it took a bit of time, of course. So you might notice it's a bit slower than running C or C++ in your browser. And the reason for that is, of course, Python does have a huge runtime. So in this case, it's actually taking a bit longer than expected. Okay, there we go. So Python initialization complete. It's using Clang under the hood, which is part of the LLVM toolchain. Then we have NumPy loaded, and it prints the result. So we can actually now run Python within the console. So here I write print NumPy array, but I actually need to prefix this with Pyiodide.run Python, and then I pass it in as a string. Yeah, 579. There we go. So now I'm actually able to run Python on the web, which I think is just great. All right, but this brings up a different question, which is we can run Python on the web, we can run C++ on the web. Can WebAssembly be used in a different way? In other words, interoperability. can we get C and Python, C++ and Python to communicate through WebAssembly outside of the browser? So what this would actually do is introduce a very nice thing, which is that different languages can arbitrarily communicate, and they're all sandboxed as well, because C++ does present a lot of risks. It's too powerful. So you might actually be able to sandbox it using WebAssembly, mitigate a lot of the risks, and then be able to communicate between the different languages. Turns out it is possible using something called WASM time, which is a WebAssembly runtime. So I'll just navigate here. Here we have a very simple C file. Again, it's simple if you ignore the boilerplate. So it's just a function that adds two numbers together. But I include this emscripted keep alive tag here. And the reason for that is it needs to be exported so that other files can use it. And this gives this function permission to be used outside. Not really, but let's just think of it that way. Okay. So now I want to run this from Python. So I'll navigate to the directory, WASM time. I'm going to open Python. I will import something called wasm time.local. Whoops. I think it's called wasm time loader. Yes, wasm time.loader. And now I can actually import WebAssembly modules as if they're Python modules. So in this case, I'm in this directory, and we actually want to first compile the C code. So let's do that first, actually. So I'm going to compile the C code. I'll write emcc add.c-s wasm equals 1 output add.js. That will compile. Okay, it compiled. It gave us a JavaScript file. We don't actually need that because we're not interested in embedding this into the web. Instead, I'll open Python again. I will import wasm time.loader. And now I can just import add. Let's just check that this is the correct file, add._underscore file. And as you can see, it's a WebAssembly module. So we've been able to import a WebAssembly module. The function that we're interested in is add. So let's do add.add. Let's add the numbers 5 and 6 together, 11. So we've been able to run C++ from Python. Now, this in itself isn't a big achievement. We can actually run C++ in Python in many ways. There are already existing options. But this allows us to do this so in a sandboxed environment where everything is secure. But also, it can extend to any other language. We can do the same with Java, Rust, Perl, Ruby, etc. Okay, so that's really the final sort of demonstration that I wanted to show you. Beyond that, what does this remind you of? Containers, because again, we have sandboxed environments. This really reminds us of containers. So this is Solomon Hykes, the guy who came up with Docker. And he really set the social media world on fire, not really, by saying, if WebAssembly and WebAssembly interface had existed in 2008, we wouldn't have created Docker because of how important it is. Of course, right now, it's not at the stage of maturity of Docker. So it has a long way to go. But think about this. First of all, WebAssembly binaries will always be smaller than Docker containers. They'll just be more lightweight. And secondly, they will always be more secure. Because Docker actually enables virtualization, it has to have direct communication with the kernel. WebAssembly doesn't have any of that. It's sandboxed. The host decides what permissions it assigns to it. So going forward, it will be interesting to keep an eye out on this and many more developments. So for example, right now we have JavaScript glue code that needs to be called. We don't want that. In the future, we'll just have a module script. We'll also have more speedups, better documentation, more serverless support. So for example, Cloudera actually gave you access to WebAssembly containers. The Kubernetes team also created something called Crustal, which is a Kubernetes implementation that uses WebAssembly. Again, too early to use in production, but interesting. And then there's a still called WebAssembly interface, which will make everything easier. Because right now I had to modify my C++ code a little bit. In the future, you won't have to do any of that. It will all be automated. So that's pretty much it. I'm open to any questions that you might have. And yeah, that's WebAssembly.
How old or new is WebAssembly?
Yeah, so around 2017, it was adopted by all major browsers. So it's part of a W3C recommendation. It's the first time really that all the browsers agreed on something, which is interesting. But it's about 3 years old.
Okay, and just a follow-on from that would be that it's obviously in 4 major browsers, if you like, support in a very extensive way, basically debugging, like, they all support debugging tools for, in particular for JS, HTML, and CSS, right? Do they also have kind of advanced debug tools for when you're using WebAssembly?
Yes, so Chrome does. I'm not sure about Firefox, but Chrome actually has very nice options. I don't have them on this current browser, just because you require Chrome Canary for now. But in the future, they'll all be in mainstream Chrome. Yeah, so you'll even have the option of actually seeing your native code. So if you've written C++ code, instead of showing you the WebAssembly text format, they'll actually show you a C++, and things like breakpoints. All of those are implemented already in Chrome. Yeah.
Interesting.
Nice one, Ramin. I really like that. I just have one question. I think I can't remember if you said it or not, but it sounds like this is the sort of thing that we would be you would use really if there was a bottleneck, if there was a performance optimization that needed that was needed, and that was kind of the use case for C++. Is kind of using it for Python. What would, because I imagine we saw it was quite slow to initialize the runtime.
Well, it's only slow in the way that I implemented it. If you hadn't implemented in a web worker, you would only have to run that initialization once, and then the next time it would load up really quickly. But again, I mentioned ecosystem. So Python has an unrivaled scientific stack, especially when you're considering TensorFlow. So you might have heard of TensorFlow.js, for example. That's implemented using WebAssembly, right? You can't run neural networks in a browser except through WebAssembly. There's no other way of doing it. And the best language for neural networks and things of that nature is Python right now. So it's an ecosystem issue. Another thing is it's not just bottlenecks, it's also security. So Rust, which is almost on par with C++. I mean, they're equally fast. Rust developers, C++ developers love to use WebAssembly just because of the sandboxing. Because those languages on their own are very dangerous. If you embed them into a WebAssembly container, you actually get security on top of that, as well as infinite ecosystem. And as you mentioned, bottlenecks.
But yeah, it's interesting, Ramin. I can see the application of this because in some of our projects with clients, we're increasingly asked to do quite a lot of heavy lifting on the front end in vanilla.js or some kind of JS framework, and often the support for numerical, doing heavy numerical computations in JavaScript. It just isn't really there, and if it is there, then it's quite slow. So yeah, I can see the benefits of using WebAssembly. That's good.
Okay, yeah. Are there any more questions someone would like to ask Ramin?
Yeah, so you mentioned that Chrome offers the ability to serve the original C++ code along the WebAssembly. But one of the things I'm thinking is that a major motivation for this is that at the moment, if you're putting code on your front end, you essentially have to give the entire public world access to your whole front end code base because all the JavaScript is plainly readable. And although there's lots of like obfuscation tools for making JavaScript hard to read, it seems to me like a lot of companies would want their front end code to be not essentially freely available to read. So do you think that might also be a motivation for companies to adopt it?
I don't really think so. I think the design philosophy that you should have in web development is front end will be readable. If you want something to be kept secret, always keep it on the back end. But as long as you want something to be open source, it's fine to keep on the front end. Also, like people did actually take advantage of this. Like I know at one point, most of the WebAssembly modules on the web were just Bitcoin miners that ran on your computer without you knowing. And existing tracking software wasn't able to find it. But yeah, so that's not the way to go.
Interesting. Cool. Thanks.
Yeah, are there any more questions?
Not from me.
Okay, yeah, great. Well, thank you for that, Ramin.
Yep, thanks.
Thank you, Roman.
Thanks a lot.
Okay, I'll stop the recording now.